Of course, the launch is something very special for space, and because it lasts a few minutes, and
it's making the data available to everyone free of charge, and by that is trying to do things like, it sounds a very big word, but by ending the hunger in the world, to feed all the world by.
Welcome back on the SpaceInfo Podcast. Here we talk about space and everything related to it. If you are passionate about space, astronomy, technology and everything about it, you can join all our social platforms at the SpaceInfo Club or our website at www.spaceinfo.club, where tons of content and a community of experts are there waiting for you. This is the SpaceInfo Club. Thank you for being here. Today we talk about space and we talk about Sentinel-2C mission, and I'm with two very special guests. I'm with Gunn Schweickert, I hope I pronounce it well, project manager of the Sentinel-2C program, and also with Remi Bellouard, project manager of the MSI instrument. So first of all, please tell me if I've pronounced your names correctly.
Perfect, thank you.
Okay. Okay, so maybe you would like to tell us a little more about what you do at Airbus, particularly on the program of Sentinel-2C and on the instrumentation.
Okay, so maybe I start. I'm Gunn Schweickert, just say Gunn in the future. I'm the project manager of the Sentinel-2. In fact, it's C and D satellites, and I've also been the project manager for Sentinel-2B already. I've been in this position for quite a while now, and before that I've been working a lot on Sentinel-2, and maybe to go even further back a bit. Yes, I've been in space here for 30 years now, working in different positions on building satellites, in principle, satellites and some bits of Ariane 5.
So Remi Bellouard, I'm what we call the chief engineer for the MSI instrument. Currently, I'm also doing the project management because the team is reduced now because we have finished the manufacturing of the instruments. So I've been dealing with the development of the MSI C and D models, and I'm also following the two instruments that have been flying for years already, so the MSI A and B. So I've been in this position for a few years now, and I'm working for Airbus since more than 20 years. Mainly on satellites. I've also worked on aircrafts when I started my career. So, but now I'm doing instruments, optical instruments, since around 7-8 years.
Wow, that's very interesting. And yeah, if you want, I would like to maybe a lot of people that will be listening will maybe already heard about the Sentinel-2C. I would say mini constellation. Maybe they know some details, but I would like to start with the letter C. So, well, that is not the first satellite of the constellation, but we know it will replace the Sentinel-2A. So what's the improvement on that side? Maybe the technological side, I would say.
Well, maybe we should not even talk about much of an improvement. It's mainly, maybe I start a little bit further back. So the Sentinel-2 satellites as such, the Sentinel-2 satellite constellation, is part of the Copernicus Program for the European Union, which is it's built on behalf of the European Union, and ESA is our interface taking care of the technical management of the satellites. And I've just been looking it up. In fact, in 2007 we started to build the Sentinel-2A and B satellites, which were then launched in 2015 and 17. And the C and D satellites have been built to secure the mission, to secure what the satellites are doing in principle with very little modifications with respect to A and B. So the main purpose is to ensure continuity of the data that is delivered by the satellites A and B. And we have launched now the C in order to secure this continuity, but not because the A or B were not operating well. They are perfectly operating, but the data is so valuable and so needed by hundreds or thousands of user communities that the European Union and ESA just wanted to ensure that there will never be a gap of data flow. So we will have the satellite B and C operating nominally in the future, and the A will still be kept in orbit in order to replace one or the other in case there's an unplanned, unforeseen problem with one of the satellites.
Yeah, so basically what can be understood is that the key point of the whole project is data availability, and also in this case data continuity, not just having something which is capable of acquiring images, but also the performance of that image acquisition is important, if I'm understanding correctly.
Yes, we have so many users that rely on receiving the data very regularly. And in fact, that is at the moment, it will continue to be like this. Every 5 days, we have a complete picture of the Earth. And so every 5 days, every user gets the same set of data again. And this simply needs to be ensured by having then 3 satellites in place, with 2 operating and 1 there to replace in case one has a problem.
Please tell me.
Maybe what I can add is that it's very important for the users also to have the continuity of the quality of the data, and to have in fact a very similar or at least almost identical performance between the different instruments. And at the moment, we are running, the testing of the S2C, and there is what we call a tandem phase. So the A model and the C model are very near from each other on the orbit, and the objective of this is to compare the data, the radiometry of the images provided by the instruments, and to ensure that we have a very, very close behavior of the different instruments.
So if I can add something for the more, let's say, technical guys that will be listening to the episode, we are more inside of the commissioning phase instead of the operative one, right? Okay, so
exactly.
Okay, so
policy.
Basically, you are using the, let's say, previous satellite as a calibration mean to set the parameters of the instruments, right?
Exactly.
It's not really it's for comparison, at least. We have inside the instrument, we have a calibration mean. We have a calibration system. So this is what we use to really calibrate the instruments. But then we compare it with various other ways. So typically other instruments. So here we have another identical instrument to compare it with. So it's of course very practical. But we compare it also with other data from other instruments. And with measurements with various techniques, or with ground measurements also, and so.
Okay.
Just to ensure that in fact the quality is as expected. So
since now we are on the topic, maybe you'd like to tell us a little more about the MSI, which stands for multispectral instrument, right?
Yeah, if you want. So. The MSI is an imager, as you already said. The principle is it's what we call a push broom imager. So for the people who don't know what that is, it means we have an array of detectors, so basically a line of pixels that is perpendicular to the orbit, or to the speed of the satellite along the orbit. And so when the satellite is moving along the orbit, this line of pixel is basically scanning the Earth over a swath which is 290 kilometers wide. And so you make long images of the Earth. It's called multispectral instrument because we are acquiring the Earth radiance over 13 spectral bands. So it's 10 bands in what we call the visible range, and then we have 3 bands in the short wave infrared range. All these bands, they are here to be able to fulfill the mission, which is mainly around vegetation monitoring, so land monitoring. When you combine the different bands, you can identify the state of the vegetation, so basically how much water you have in it, or how much chlorophyll you have in it, or you can identify between various types of vegetation. So it's the main goal of all this set of bands that we are using. And just for you, so the resolution we have is between 10 meters on ground, so 10 meters and 60 meters. So it depends on the band. So you can imagine over a swath of 290 kilometers, the amount of data that we get when we run, when we perform these images in the 13 bands. It's quite huge.
Yeah, sure. Yeah. Indeed. I'm sorry. Yeah, please tell me.
Yeah, we acquire some 1.4 terabit of data per orbit, and an orbit is 100 minutes. So you can imagine how many, petabyte we have collected over the years with the 2 satellites.
Yeah, and also I was very curious about also the ground transferring of those data, because 1 hour 100 minutes, right, is an orbit, so you must be also very fast in switching the ground station, I suppose.
Well, yes, we have as 2 of the other main features of the satellite. The one big challenge is, of course, the instrument, but the other 2 challenges are, first of all, the accuracy of looking at the data and being sure about the place you look at, which requires a good AOCS system. And the other one, and there we come back to the data, is we have to handle this huge amount of data, first of all, on board of the satellite. We have a very sophisticated mass memory formatting unit, which is, by the way, also built by Airbus.
Okay.
And here in Friedrichshafen, by chance. Then we transmit the data on 2 parallel routes. One is by an X-band system, and the other one is by what we call the optical communication payload, which consists of a laser link, laser terminal that sends data to the EDRS satellite, sort of data highway. And then from this geostationary satellite sends it down to the ground station. So on every orbit we have two separate means of transferring the data, and by this relay satellite EDRS we have the very constant capability to send it to the related ground stations.
Yeah, that's very I think that a lot of people don't weigh much this topic, but once you acquire the data, you also have to be able to download it on the Earth, otherwise they're basically wasted. You have to delete it, I suppose. So that's very important. Also, I would like to let's say, while we are on this topic, you mentioned at the beginning that the community, the people and the companies that access this kind of data are very wide and also different. So how is working with such a variety of companies? Maybe, you are in this sense, maybe you let's say you are a service supplier, so there is a direct interest from the companies to acquire their data. But I also think that while building the satellite and also the constellation, you must have worked with a lot of different realities.
maybe that traces very much back to the development of Sentinel-2A and B satellites. So the major user communities, and I think Remi was already pointing in this direction, is very big. Or maybe let me start with more explaining what we do and what the Sentinel-2 satellites do. They are out of the Copernicus missions, the Sentinel-2 satellite, out of Sentinel-1, 2, and 3, that is with the starting satellites. The Sentinel-2 is the one concentrating on the land masses of the Earth.
Okay.
So with the optical instrument, we have a look at or continuously circle the Earth to get a complete image every 5 days. And that is, concentrating on the land masses and coastal waters, islands. So all these are looked at, and there a strong emphasis is on agricultural exploitations, on forestry, on land usage, on some disaster management, for avalanches, for earthquake, etc. And then you can imagine, with a 5 days repetition of the complete picture, the major use is really to detect changes. So by looking at the same spot 5 days later again, you can see how things have changed. And for me, still one of the most fascinating applications is really agriculture, where the farmer, once he has put some seed on the ground, after 5 days, due to the excellent capabilities of our instrument, he can see how the seed has developed within 5 days. He can judge on the chlorophyll content of the plant how that has changed just after 5 days. And by this, he can then say, okay, I need to, it's been good or not so good. I have to add this much water. I have to add this much fertilizer. So real day-to-day applications, and bringing very much use to the farmers, and by that to the complete world community. In fact, that is part of the background why the European Union has asked us to build these satellites, and it's making the data available to everyone free of charge. And by that is trying to do things like, it sounds a very big word, but by ending the hunger in the world, to feed all the world by having the adequate food, by securing how a farmer exploits his field.
Yeah. Also, one of the things I'm always thinking about while talking about this topic is that space is seen as, let's say, the farthest outpost of humanity, where technology is at its top, everything must be an excellence, and then you can get a service from this kind of technology and use it for the very first activity that the human being made in its history, which is agriculture. So I think that if there is one of the biggest benefits of space here on Earth is this, for example. And and also you mentioned the European Space Agency as a partner. I don't know if it's more of let's say an enabler, if let's say this kind of service would have been possible without let's say a sovereign entity or not, or how is the partnership configured in this sense?
Yeah, maybe just to add on the last topic before we come to this. For the agriculture, to bring it to the end, the farmer on his tractor, he's got a a program telling or already programming how much water he has to put will be put on the field, and that's all. So it's really end-to-end application, starting with the data of the satellite being transferred to ground, being processed, being further prepared by some user company, by some tractor running company, and then bringing it to the individual farmer, and he just has to go and have everything done automatically. I just have to add this because I really think it's a great thing when you think about it.
Yeah, also thinking about something which is soaring at kilometers above your head, and it's capable of looking so close to what you're doing. It's so powerful.
Yeah. In fact, it's 786 kilometers above us. So back to the question of the European Union. Well, it's the European Union who had these ideas to start with. So they have had the idea to do something good for the world, to solve problems of the world. And maybe in the beginning, they very much concentrated on things like agriculture. Nowadays, you can see them very much exploiting the Sentinel data for anything towards climate change. Of course, it was already there also 20 years ago when they started the programs. But I think nowadays, every other day you see on television, you see everywhere that Copernicus data are used to monitor climate change. And yes, so it was the original idea of the European Union, and they went to ESA as a facilitator, as someone who is used to working with industry in building satellites, and ESA has prepared the technical requirements, specifications, and we are through ESA, or we have ESA in between the European Union and us. And together with ESA, we have designed, developed, tested, built, and in the end delivered to ESA these satellites, and which the sea is now the third one of.
Okay, I didn't think about that. That ESA could would have developed also up to the technical specification point. Actually, I thought only that they could give, let's say, a sort of idea, or I wouldn't say conceptual design, but something of that way. But this gives the idea of how deep also the space agency go when designing this kind of technology, I think.
Yes.
In fact, during this, during a project development like that, you have several phases. So you have a study phase at the beginning, which is more a discussion on around concepts and around specifications. So basically, what happens usually is that you build the specification as a co-engineering between the agency, who knows the need of the final customer, and with the industrials who have experience of detailed design. And so it's a co-engineering with the agency, and of course the agency is also in the end, in charge of the performance, the overall performance in front of the Commission. So they have to have a good idea, of course, of the quality of what we are delivering. So that's why they also have to go into the technique. That's normal. But I think on this project, what was good is that we had a very good cooperation with ESA, and so I think it's really important in such complex programs, because you always have issues, so you always have to discuss, eventually negotiate some points, and this you need to do it in a practical, pragmatic way to be able to to fulfill the objectives of the mission, and to, in particular, in terms of schedule, which is always complicated in such developments.
Actually, a couple of words that made me think while you were talking. The first one is the word performance. I'm coming from. I've studied this kind of field at the college, but then I've been working in the aviation field. And when we take requirement, they are usually safety related or things like that. You have to grant something, but you don't are really responsible for the performance of what you're building. You're just saying, okay, I built something which works, but I'm not always granting that it will work at some kind of performance. And saying that that satellite in general, something which flies in space, has to grant a minimum performance, gives the idea of how much complicated. Also, I think about also the responsibility of the people who are building it, and then have to grant this kind of this performance.
Yeah, it's one of the major points. The major difficulty we have on space developments. And so at the beginning, you do a lot of paper to demonstrate on paper that you can performance that are required, and then we do a lot of testing on ground also. And so with a given representativity of the testing, of course, it's not exactly always test as you fly, but usually we are quite close to in terms of representativity of what we will reach in flight. Of course, you still have a bit of uncertainty. So when you get the first images of the instrument, when just after launch, of course it's great, and it's also a relief. It's the only moment where you are fully sure that you have not missed in the end.
Yeah, indeed. I was wondering which are the biggest uncertainties or issues that you may encounter. Maybe, for example, for an instrument on board, I'm thinking about the launch, when vibration and the environment could threaten the instrument, but maybe I'm wrong.
Yeah, so of course the launch is something very special for space, and because it lasts a few minutes, and it's the most stressful part that the satellite and the instrument will live during its whole life, and it's just a few minutes of its lifetime. But of course, we have to do many things to support the launch. And so there is some standard testing that we do in the space industry to check that the launch will be okay. So you do vibration testing, you do thermal vacuum testing. There are usually complex tests where you do also so you check the thermomechanical behavior of the instrument, and usually in thermal vacuum you also test the performances. So it gives you a good confidence that the launch will happen properly. Normally, I'm not really aware of you can always have issues, but normally we are quite well covered because of the ground testing, because of course on ground we kind of over test compared to what will happen during the launch. I don't know, Gunn, if you want to. That's something.
You're right. The launch is a very exciting moment for the project managers. We've just had the launch of the Sentinel-2C on the 5th of September this year. So, and even though, as Remi just explained, we have a good and thorough testing, very sound approach with many margins implemented, it's still exciting to see. First of all, to see the rocket lift off, and that is really the moment when you get relieved. Is when you see your solar array deploys and you get the first contact with your satellite. So even if you're really sure you have built an excellent satellite here and everything is fine, you're still relieved and happy to see it has done its job, or you have done a good job in the end. The proof is in the pudding.
Indeed. I was going to ask which was the most, let's say, I wouldn't say stressful, but the demanding operation, and it seems to be the array deployment.
Well, that's for us well, as my background is a mechanical engineer actually, and we always say no mechanism is a good mechanism. So anything that has to deploy, or sort of any mechanism that has to work, you're always happy once you can be sure it has worked. So
on the MSI instrument, you have a mechanism because you have a door basically that protects the instrument during the launch, and also and also on this door you have a diffuser, which is a white surface which we use every month to calibrate the instrument. So the door moves every month. So on the door you have a mechanism which is just a small pin that we use only just after launch to release the door. And of course this one has to work. If it doesn't, then the instrument remains closed and you don't do any image. So of course it's a bit stressful when you activate it just once in the lifetime.
Is the enabler of the whole mission, I think.
Yeah, if that doesn't work, then everything is lost. Yeah.
But then you were asking about challenges. Maybe I can say a few words on challenges on instruments or optical instruments. So one of the big challenge we have on optics is the mechanical precision that we need. So basically alignment of the different mirrors that we have on a telescope. So inside the MSI we have a telescope which is made of different mirrors. And so to give you an idea, all the parts are more or less aligned with a precision of around 5 micrometers. So you have big mirrors, so 50 centimeter wide, which are aligned at this level of precision. So that's one thing. And then the polishing of the mirrors is done at around roughly 20 nanometers. So it lasts very long time to polish the mirror. So it gives you an idea of the kind of challenges we have. And it's also, we have some thermoelastic, so all the instrument is regulated thermally, and to avoid movements of these optical parts in flight, you need to regulate the whole thing much better than 0.1 degree all the time in an environment that is of course changing, and because you have eclipse parts of the orbit or sun parts. So these are optomechanical aspects are very challenging on optical instruments. Maybe what I can add also is cleanliness topic. So everything needs to be built in a very clean environment. So this is mainly a big constraint for manufacturing. So for the people who are integrating the instrument, so they have to be dressed in a very uncomfortable way all the time when they work. So I think this has to be mentioned also, because I mean the people who do the design have many challenges, but it's also very difficult to integrate and to manufacture, because you have all these constraints, a lot of precision, and so these dressing aspects. I mean, I've tried it a few times, and to be fully dressed with you see only the eyes, and basically it's not very nice. And when you stay 2 hours like that, so it's also part of the work. And I think it's important to when we have built such instrument, it's a very big teamwork, and you have all these people building it, which take a big part on the project.
You mentioned also the temperature range in which the whole satellite varies along the orbit, but aren't you also concerned about the still in the environmental let's say field, but about, let's say, particles, or I would say almost debris, but I don't know if the debris are actually a danger at that altitude, or how do you manage also the other factors of the environment?
Well, debris, we have of course the risk of collision with debris that is there, and for that reason, all major parts of debris are controlled by the European Space Agency. And if there's debris coming along, then in the end we have to fly the occasional maneuver to get out of the way, to have it, to avoid a collision. So this is certainly the case, but well, for the cleanliness itself, in principle, it's fairly clean up there.
Okay, so it's still a clean orbital slot. Okay.
Yeah, well, we have to make sure, as Remi said, on ground, that we don't pollute mainly the instrument. For the rest of the satellites, it's not so critical. It's mainly the optical instrument that really needs to be very well protected in terms of cleanliness. The complete satellite is built under clean conditions in a clean room, but for the instrument itself, we have even higher restrictions. So we have an ISO 5 requirement for the instrument and an ISO 8 for the rest of the satellite.
Okay, I don't know. I've seen that you, Remi, were adding something. I don't know.
Yeah.
Yeah, what I can also mention that we have one part of the instrument, so the one that is the focal plane that is acquiring the short infrared bands. It's cooled down to minus 78 degrees Celsius all the time, and so as it's a cold part, when you have molecular contamination, you can have continuous outgassing of these molecules inside the satellite all the time. And it goes trapped. It is trapped by cold parts. So cold parts can, if the molecules go, they fly around inside the satellite, and they once upon a time they go on a cold part and they get stuck there. And so if this happens, you get a loss. If this happens on the detectors, which are cold, you get a loss of transmission. And so what we do now once a year on the instruments that are in flight, we do what we call a decontamination. So we heat up the focal plane during something like 24 hours or a bit less, and this releases these molecules that are on the focal plane on the detectors, and so they go away basically, either inside the instrument or completely away in space. And we recover the transmission of the instrument. But to be sure that you don't need to do this too often, you need to have a clean satellite when you launch, basically. So this is why we have to ensure at the end of integration that we have all the processes allowed to have a minimum level of pollution, of contaminant.
And along the integration or building and integration process, we continuously measure the cleanliness, of course, and have, if necessary, some sort of cleaning even.
Okay. I think this is a very delicate topic. I don't know, but also I thought that there were a sort of vibration or mechanical, let's say, means to keep clean the mirrors and all the parts. But I would have never thought about heating things up, actually.
Well, as I said by Remi, the temperature of part of the instrument is that low, and a cold surface, as you can imagine, things stick to cold surfaces. So it just collects. It gets stuck there. If you have particles, they get stuck on the cold surface. So to get rid of it, or to not let it happen in the first place, you need some heat introduction.
Yeah, like when you are cooking some food on a pot, basically. I think it's the same. And if we can now change a little bit the topic, I would like to remain inside of the Earth observation field, but more under, let's say, the strategic point of view, because we are all seeing that more and more companies, public and private ones, are trying to develop a smaller or bigger constellation to observe Earth and acquire data from it. And I don't know if there is already a sort of competition in this sense, or it is still, let's say, a privilege of a few.
Yeah, and on the Copernicus program, it's all of European industry that is participating. So starting with the first 3 satellites. It's the Sentinel-1 is more a Thales satellite, the Sentinel-2 is more an Airbus satellite, and the 3 is a mixture of the 3 of the 2 big competitors in Europe. And talking about when you look into the country contributions of the different countries, like our Airbus Sentinel-2 in Friedrichshafen, we are the prime contractor for that, Friedrichshafen, Germany. And the MSI in Toulouse is the major contributing company as with the instrument. And the platform is from all over Europe, more or less. So, competition. Of course, there's competition in between the companies within Europe. But as said, the Copernicus program is giving everyone a chance.
Also at the beginning, Remi, you talked about how is the, let's say, the optical bandwidth and also the infrared bandwidth used. But do you think that in the future this bandwidth will be enlarged? Maybe it's useless, or maybe we can use, let's say, the observation in the infrared. In the ultraviolet.
No. So what I can tell you, you may know that there is currently a study for Sentinel-2 next generation. So there is a study phase that has been launched by ESA for since a few years already, and so we are discussing with them the next generation specifications. And so the main differences from what I heard of, because I'm not working directly on the project, but I heard a bit about it. So main differences are around the resolution on ground. So instead of a minimal resolution of 10 meters, they are expecting, or they would like to go down to 5 meters. So which has a huge impact on the instrument, because you in terms of radiometric level, so you need to increase a lot the number of pixels, and also you get less radiometric signal, so you need to increase the size basically of the instrument to get more flux. And also to answer to your questions, I know they are asking for more spectral bands. I think the range is similar, so it's from the minimal to the upper spectral band, but they are asking for more granularity. In the end, more bands, so more pixels, more complex instruments
to build it.
Basically. Exactly, and more also.
A challenge.
Now I would like to ask you about one last question, because I know that a lot of people that are listening to this podcast are also young professionals or young people who are dreaming about working in the space field. So maybe you'd like to tell a little more about your career, how you started, and how you are going in your career. What are your dreams for the future, so people can get inspiration and try to work in this field?
Okay.
You want to start, Gunn, or?
Okay. I'm the older one, so I start. Maybe I have a bit of a not 100% typical background. I studied math and engineering at university. The engineering part, I got in contact with Airbus, and then straight away writing my thesis already in Airbus, and I got stuck there because it was so exciting, I would say. I'm sure still many young people have the same fascination about space. So once you get in contact with anything to do with space, you just get infected by the virus and find it's so exciting. So yeah, I started then working here as a mechanical engineer in the mechanical analysis department, and via that gradually took on further responsibilities: mechanical thermal engineering, system engineering of a satellite, and in the end became a project manager. What can we say? Young people, it's apart from the fascination of the subject or the object itself, what is really exciting is the working environment. It's a very international environment. So you're working with people from all over Europe and sometimes also outside Europe, and just this working together and also the cultural differences you see there, and the youngsters. With all the differences, you see how the people in other countries have the same problems as in your own. This is a very also rewarding part of the work in space, I would say.
And what about you, Remi?
Yeah, so I started, I did some engineering studies as Gunn, so in France and in Germany. So I had already an idea of having a career in a company that works in an international environment. So I did a specialization in aeronautics and space, and I started at Airbus on aircrafts, and I had the chance to go to work on flight mechanics on the A380 program for the complete development, so from the paper phase to the flight testing. And it was really great. And in the end, I decided to go to the space part of Airbus because I thought I wanted new challenges. And also what I liked in the space industry is also the impact of the space industry on some important topic like science related to climate change and this environment and so on. So this is one of the reasons why I went there. And so in Airbus space, I did many different things. I started in the integration field, so in the manufacturing. Looking at tests or managing big tests, environmental tests of the satellites. And then I did different things. I worked on microwave instruments, and I ended up in the optical instrument division, which is, I think, really great because there is a huge variety of instruments that we are building. So with very different challenges, and it's always complicated, but it's always different. So you learn all the time. And so I think what I would say to a young engineer who wants to start in the space industry, I think what you can be sure of is that it's never boring. You can work on many different topics, and if you like the technique, you can learn your complete career. It's from that point of view, it's really interesting. And I also, as Gunn said, I think what's really great is this international environment that you have in this industry. You keep working with people from everywhere. On every project you work with, almost you work on almost it's very international. So
yeah, so nice. I think that anyone can get inspiration from this. And I want to say thank you to Bot, and also to all the people that are behind the camera that helped us organize this episode. So thanks a lot, and I hope to talk with you again soon. Thanks.